Welcome to solverfy.
For this problem on the topic of oscillators, we are shown a mass M connected to two springs with spring constants K1 and K2. The mass is connected to these two springs in two different ways as shown in figure A and B. We want to find the period in part A as well as the period in part B by ignoring friction. Now in part A, if the block is displaced a distance x to the right in figure A, then the length of the spring will be increased, length of spring 1 rather will be increased by a distance x1, and the length of spring 2 will be increased by a distance x2. And so the total increase in the length of the spring, the effective spring, is x1 plus x2. We'll call that distance x. Now the force on the block we can write as F, and this is minus the effective spring constant of the two springs in series times the total expansion x of the springs. Now because the springs are massless, they act similar to a rope under tension, and the force F is exerted by each spring. And so this equation here is minus K1 x1, which is equal to minus K2 x2. And then we can use the fact that x is equal to x1 plus x2 and write this as minus F over K1 minus F over K2, which is simply minus F into 1 over K1 plus 1 over K2. But we know x is simply minus F over the effective spring constant K EFF, which means that 1 over the effective spring constant is equal to 1 over K1 plus 1 over K2. And so therefore the period T, which we know is defined as 2 pi times the square root of the mass M divided by the effective spring constant, can be written as 2 pi times the square root of M into 1 over K1 plus 1 over K2. And so the first period for the first configuration is proven. Now in B, we want to show the period for the second configuration, and here the block will be in equilibrium when it's stationary, and so the net force at that location is 0. Then if the block is displaced by a distance x to the right in the diagram, spring 1 will exert an additional force of F1 is equal to minus K1x in the opposite direction to x. Likewise, spring 2 will exert an additional force F2, and F2 is minus K2 times x in the same direction as F1. And thus the net force on the displaced block we'll call F, and F is equal to F1 plus F2, which is minus K1x minus K2x, which we can write as minus K1 plus K2 times x. So the effective spring constant here is K, and K is simply K1 plus K2. And this means that we can find the period T, and the period T is 2 pi times the square root of M over K, which is 2 pi times the square root of M divided by K1 plus K2 as required.